pretty much review material of very basic foundational stuff, right? And the second test is when you start getting into the core topics of things that might not be immediately something that you can call. And then the third test and fourth test frequently are the ones where you're knee-deep in stuff specific to just this subject, and so it requires a lot more effort, and a lot less of it is going to be there because you remember this from way back when. So how do we, I hear the test number 2, I guess, from the general consensus was that it was a little bit harder. Was there more math this time than the first one? About the same math? Did you pull your calculator out? That's about the same number of times?
It's definitely more as far as like figuring out how to really solve the problems.
Okay.
Because there was like all of the stuff that you taught us, but then there was like, he actually did teach us, but it was like very quick. So it kind of threw me off a little bit.
Okay. Could you still identify the variables that you needed?
At times, yes. At times, yes. And then at times,
Sometimes
like,
no.
yeah, it wasn't just that. It was like I was in a weird headspace.
Well.
And I can't blame it on that, but I mean, as far as like the test goes, it was a difficult test. It really was.
Like I said, as we're getting into some specifics about chemistry, there's not going to be a lot of situations where you're going to need to be able to do math about pH and titration outside of a chem lab.
Yeah.
And that's just a reality of the class. I don't get to define the learning outcome, so balancing and titrating equations is one of the learning outcomes for the course. So I think it's still an important foundational understanding of chemistry, so I don't know that even if I could, that I would get rid of it. But yeah, I can see how it could be harder. The average was definitely lower. Not significantly lower, but lower. It doesn't make me worried about everyone's grades. There's one or two people that I might send an email to, be like, how's it going, that type of stuff. But beyond that, you would be doing pretty well. That's what the homework is there for. I am noticing that people are doing better-ish on the homework. As far as like doing one attempt and waiting, recovering, double-checking for the second attempt, which is good. That's what I like to see. I would love to see everybody getting 11s and 12s and all the homeworks as we move through. That gives you a little bit of a bump, since all of those things add up to another exam, right? So even if you do have an exam that's not so hot, you get a bump from a really good homework grade, and that can bring up your average. Not by a lot, since that's the way averages work, but you know, by enough that it might make a significant difference.
Is the exam released to you yet?
It should be, yes. Monday evening, I opened it up for viewing, and that's because Monday earlier that evening I was in a car. So my Memorial Day activity was driving to Minnesota with my 2 young spawnlings to see some aging relatives in Minnesota and spend some time with their not-so-aging cousins and whatever you would call children of my cousins, whatever that is. Second cousins? Sure. I never really had it. Yeah, it's like, what is it, first cousin once removed? I don't, like all of that just never, I've had it explained to me multiple times. It's another one of those things where it just, evidently I don't care enough to remember the answer. So, but anyway, they're her cousins and their second cousins, whatever. Playing a lot with that. And then, that was Saturday, and then Monday I drove back. So, very dense weekend. But unfortunately that also meant that I couldn't really get in and change your exam view until Monday night, so there you go. I did not notice anyone took it late, so good job there. For at least taking, I did notice quite a few people took it very early on Friday, surprisingly so. That was probably just so that you wouldn't have to worry about forgetting it when you come back from a flow trip, half trashed on Sunday or something maybe.
Some testing centers open?
That too. There were like 3 or 4 students that had it done. By the time I looked to see if it was active and working, like 4 people had already finished it or something like that.
Hey, how was Solo?
Solo was good. I enjoyed it. Evidently, it is not receiving the same critical acclaim from others. It's actually the worst Star Wars opening so far. Yeah, it's cash-wise, as far as like how much money it brings in, ticket sales. So I don't know if it's from. There's people arguing about if it's because of Star Wars fatigue or if it was because of all the bad press it got during initial development that people couldn't really get excited about it. And so, I don't know, but I enjoyed it.
Star Wars fatigue.
Well, we did just have a Star Wars movie, like not even 9 months, actually not even that 5 months, because there were people, you could still get Last Jedi in January, so.
And it is fatigue. I didn't go to Last Jedi. I'm just tired.
Right, you
I
say
saw
that.
the original in the theater, 1978, and
You say that except that people will go and see Marvel superhero movies that are 3 months apart.
Yeah.
That's true.
So it's like, but the argument there is, yes, but that's because different directors can give it its own tone, and so every movie feels like its own movie, even though they are all connected, whereas Disney has such a tight, Disney and Lucas before it had such a tight control over Star Wars that it doesn't really feel like it's new and fresh and something different. It's just kind of moving the story on, and so if you got your Star Wars fix 5 months ago, maybe you're not quite so jazzed to go drop another one. Maybe you also would rather spend your money on, Avengers 4 or Deadpool 2. So there's a lot of trying to double dip with who it is they're marketing to. There's a lot of excuses about why maybe they didn't do so much. But I enjoyed the movie.
I wouldn't be fatigued.
It was fun.
If they'd stuck remotely to canon and not gotten rid of all the keys on, all the stuff.
Oh, you mean Disney canon? As opposed, I was trying to think of what aspect of Han Solo's history that they
No, I meant
changed.
Last Jedi.
Right, yeah, there we go. Okay, well, that's a little different. All right, so let's talk about chemistry. We have chapter 11 to get through today. I went and double checked when I was kind of plugging through the syllabus and figuring out how things would be going. It used to be a section where some of these organic chapters would take multiple days. I spaced them out 1 chapter a day like everything else in the syllabus. We'll see if we actually stick to that. The chapters aren't that long, but like I said during the pseudo intro, these chapters are also much more dense with information that might be relatively new to you. And so we may need to, if there is a request, we may need to go back through and do some of the practice problems and do a little bit of in-class practice. That's also what the homework is for. This is going to be a joy for me because I'm not sure how I'm going to actually do homework. This might be one of those, like, maybe give you something, like a sheet of paper or email you a PDF or something like that. I'm not sure, just as far as like what's the appropriate way to draw this thing, or what's like that type of thing. It's going to be a bit tricky on a chapter where the vast majority of the chapter is all about naming hydrocarbons. So I don't know how that's going to work for a multiple choice homework question.
I'm just wondering about the test too.
Yeah, well the test means I'm going to have to spend a lot more time. That I'll have to be more picky, but it does mean that it's going to limit how I ask questions. And so for example, I can guarantee you there won't be any draw this molecule questions on the test, right? But I can do the flip side of that where I give you a molecule in 4 different names and say what's the correct name, right? So it does mean based on the format of these exams, it is going to limit and therefore inform the way that you should study this material, right? So being able to manually draw all of this will not be nearly as critical as being able to accurately name something that has been drawn for you. That being said, if I was really feeling up to it, I could also give you a multiple choice question where all of the answers were links to tiny little images of structures and asked you which is the correct structure for this oddly named hydrocarbon. I don't know if I'm going to do that or not. But it does mean that I need to get a head start on the test bank for this chapter for exactly that reason, because it's going to be a lot of work for me to develop that test bank for you so that we don't all have the exact same questions on the test. So, Let's talk about the chemistry of hydrocarbons. There's a reason why, and just even beyond just general knowledge, there's a reason why knowing something about this type of material, about organic chemistry, is important. Exposure to different chemicals, whether or not they are fire hazards or otherwise, it allows you to have a better understanding of what potential dangers there might be based on what you're being exposed to, what someone was exposed to before they were brought to you. It's something that emergency personnel have to worry about, so much so that if you're running a lab that has these types of chemicals in it, the shorthand for emergency responders, at least the lab that I was running, was that you were supposed to keep a booklet with the common and scientific names of all of the chemicals that you had in your lab, and you're supposed to keep that near the easiest access to the lab that you're working in. Ostensibly, the argument there would be, I guess, that if you were a first responder, a firefighter, or otherwise, and there was a fire or some sort of emergency in the lab where chemicals had been spilled, that they would take the time to open up the notebook and flip through to familiarize themselves with all of the chemicals and the dangers of said chemicals before they would walk into the room.
You want to know how we're trained on that?
Sure.
It's called, you see green smoke or anything like that, back up till you don't see it. Because it's not our problem.
Right, yeah.
It's exactly what we're taught.
Mm-hmm.
We wait till hazmat comes in, because how are we going to help anybody if we're walking into that and we fall down?
Yeah,
No,
exactly.
you can't.
There's
Right.
just more, more bodies.
Right.
So-
But there's a lot more to be worried about in a chemistry lab than green smoke.
Yeah.
So, I mean, the statement that I was making was a bit facetious for a reason, because as a firefighter, you're either going to make a split-second decision to run into a room, or you're going to make a split-second decision that it's too dangerous and you're not going to go in. What you're not going to do is reach around the corner to grab a notebook and start flipping through the pages.
We were also taught if the firefighters are falling and the police are falling, because they're always the first to jump into
Right.
anything,
Then
back up.
right,
Yeah.
yeah, for the same reason. You can't
Yep.
help anybody else. Same reason why people get mad about people who crawl into buildings that are collapsing. It's like they're trying to save lives, yes, but if the building isn't supported in a way where it's not just going to collapse on top of them, all you're doing is increasing the body count when it comes down on top of you. So, there you go. But still, ignorance is never the solution. Not knowing that the cliff is coming will never prevent you from driving off of it, right? So knowing about these chemicals, the nature of them, what it means with some of these naming conventions, is going to empower you. Whether or not it empowers you in a split-second decision about walking into a chemistry lab where there's a fire or someone passed out, that's a bit more of a general argument.
Knowing is half the battle.
What's that?
Said it, knowing is half the battle.
Knowing is half the battle, G.I. Joe or otherwise, you are correct. Like I said, ignorance is never the solution. Knowing might not be the answer either, but ignorance is never the solution. So, in my opinion, I should say. Organic chemistry is the study of organic compounds, which are by definition carbon-containing compounds, or compounds that contain links between carbon and hydrogen that have as their primary constituents. An example of an organic compound that we've already discussed somewhat at length is vegetable oil, which is a carbon and hydrogen or carbohydrate containing, well, oils and lipids in this case, not so much carbohydrates, but still a carbon containing molecule, so it's an organic molecule. There are some significant differences in the physical properties of these organic molecules with respect to non-organic characteristics, which is what we're going to come up with in just a minute here. So, what are some of those properties? An organic compound made from multiple carbon and hydrogen atoms. We can add in a few other things as well, so you can get some oxygen, some sulfur, nitrogen, phosphorus. One of the other groups that is very easily and commonly modify organic molecules are halogens, so chlorine, bromine, iodine. You get common products that you guys run into on a daily basis: gasoline, a lot of medicines, most medicines, shampoos, plastics, perfumes. All of these things are organic compounds, or start as organic compounds with respect to the fact that they are carbon and hydrogen as the majority component of their chemical structure. But that does not mean that all plastics are organic molecules with respect to coming from life, which is one of the reasons why we have such a problem with the plastics that we make now. Most of the plastics that we make now are so synthetic because they do not come from anything that life creates, and if life never creates it, then life never had a reason to learn how to digest it, and they haven't been around long enough for life to really figure that out yet. So we talk about the plastics that we have now lasting for millions of years in landfills, and that may very well be true, but throughout the course of those millions of years, we might also end up with the evolution of something, probably a bacteria, that can actually break that stuff down. So the overall impact that we're having on our world might be less than what we currently believe it to be, but we have no way of knowing what that future might hold, and whether or not that bacteria then destroys all life as we know it, based on by eating all of the plastics that our life depends on. Wouldn't that be awesome? So, when we write the formulas for organic compounds, we write it with carbon first, followed by hydrogen, and then any of the other elements that are involved. C6H12O6. So we then add things after that. Organic compounds typically are made out of covalent bonds. You can get organic salts, but that's still going to be a large organic molecule that is ionic in some fashion. But it's still going to have a whole bunch of covalent bonds holding the organic part of that together versus the ionic interaction with the non-organic salts. They typically have low melting points and boiling points, which means having a low melting point and boiling point means that they will boil and or melt at temperatures that we would consider low or reachable, which is why when you talk about oil, it is a liquid at room temperature because it melts from a solid to a liquid at temperatures that are below what we find in everyday life, so easily accessible temperatures. A low boiling point would mean that we actually have the form of these organic molecules is not even a liquid at room temperature, but a gas. Can someone name an organic molecule that is a gas at room temperature? Do you guys have ever burned methane? Do you have propane? Stoves, perhaps? So we have molecules that are organic that are not even liquids at room temperature, but are actually gases at room temperatures. And we're going to understand where those cutoffs are for which molecules would be gases at room temperatures, which would be liquids. We do have some solid organic molecules at room temperature. What do we call a solid organic compound? What's a common name for a solid organic molecule at room temperature? Give you a hint. We get some of the naturally occurring stuff from bees. Honey is what they eat. That is an organic mixture, yes, but they make their homes out of wax. So organic compounds that are solids at room temperature are frequently, as a common name, are just waxes. And we will talk about some examples of those. There is another organic molecule that comes in a solid at room temperature, and it's called margarine.
That's not a...
Yes, it is. It comes from organic sources. We have just chemically altered it so that it's a solid at room temperature.
Correct.
Margarine, as opposed to butter is animal fats, which are also organic molecules. Margarine is a plant fat that has been modified, so instead of being an oil at room temperature, it's a solid at room temperature. And that active modification to create that solid also frequently creates something that's somewhat problematic, but we'll get to that when we get to it. So, inorganic compounds tend to have high melting points, high boiling points. When was the last time that you ever heard anybody refer to gaseous salt? Which is a very different thing than gaseous chlorine, right? But sodium chloride does not turn into a gas until relatively high temperatures. Propane, on the other hand, is an organic compound that we use as fuel that is a gas at room temperature, but salt is a solid at room temperature, right? So its melting point to turn from a solid to a liquid is quote-unquote high, which means it is well above temperatures that we would easily and commonly reach in our everyday lives. So here's a lovely table that takes a lot of information and condenses it into a relatively easily accessible slide and or page in your book. It talks about organic versus inorganic molecules. So we have organic molecules here on the left, inorganic molecules on the right, with examples of both, talking about what elements are usually present, what particles we have here. So organic molecules usually contain molecules because it requires multiple atoms put together to get a carbon-hydrogen compound, right? Whereas inorganic usually contain ions, so those charged particles, or sometimes polyatomic particles still, but charged molecules. Bonding mostly covalent versus ionic. We have the polarity of most organic bonds are non-polar unless we have a very strong electronegative atom. Refresh my memory, what would be an example of a very strong electronegative atom? We just had this on the test. Where would you find strong electronegative atoms? On the upper right or the lower left of the periodic table? Upper right. Oxygen, fluorine, chlorine, nitrogen. Strong electronegative things that like to hold on to electrons. Instead of sharing them relatively evenly, they hold on to them very tightly, creating this dipole. It gives us those partial positive, negative charges. You know, the thing that gives water the vast majority of its special properties, that makes it the amazing liquid that it is when it comes to sustaining and being required for life. Those types of things. So that's the polarity, mostly non-polar. Our melting point and boiling point are usually very low, usually very high flammability, and not very soluble in water for our organic compounds. So, hydrocarbons as a group are named so because they combine both hydrogen and carbon. If we have a hydrocarbon specifically, then we are talking about a group where that is the only thing that is there, hydrogen and carbon. We can have saturated hydrocarbons, where we have taken all of the carbons that are present and we have applied the maximum number of hydrogens as is reasonably possible. And by reasonably possible, I mean if you use the Lewis dot structure, right, of pairing up those electrons in the outer valence shell of carbon, what we want to do is make sure that we have 4 lines coming off of every single carbon molecule and 1 line connecting every single hydrogen molecule. So if we have single bonds between all of the atoms involved in a hydrocarbon, then it is a saturated hydrocarbon because there is no more room for anything else to be added on to this molecule. At least without adding a considerable amount of energy. So if we're going to have a hydrocarbon that we describe as being saturated, that would also imply, and we have specifically stated previously, that there is another category of hydrocarbon which would be unsaturated. There's even polyunsaturated hydrocarbons. So how could we take this saturated hydrocarbon and make it an unsaturated hydrocarbon? Remove hydrogens and replace them with what?
Anything else?
Not so much anything else, but with respect to dietary hydrocarbons, yes, anything else, but specifically, we replace them with double bonds, or even potentially triple bonds. We'll get to that in a minute. So here's an example of methane, a very simple hydrocarbon. It's simply 1 carbon and 4 hydrogen atoms, covalently attached to each other. Because of this, we have the standard tetrahedral structure, where we have a 109-degree bond angle between all of those hydrogens, right? Here we have the space-filled molecule. B is our ball and stick model, so it's kind of a hybrid between the space-fill and the just regular stick model. It gives us a 3-dimensional structure. C, we have the wedge dash model as opposed to D, which is the expanded structural formula or the condensed structural formula here on the right. Now, this one, these last 2 on the end, we can probably very easily understand what is going on here, right? We have 1 carbon with 4 hydrogens surrounding it. Each one is combined via a single dash, meaning a single bond. We could have drawn this with the Lewis structure where we put dots on either side of this line, right? We wouldn't even need the lines if we were going to do that to illustrate those 8 valence electrons around the carbon and the 2 valence electrons around each hydrogen and how they share them to form those covalent bonds, right? So that's similar. We can see that. we can then shrink this one, D, down to E by just getting rid of the bonds and grouping all 4 of the hydrogens together. Why do the hydrogens come second? Because when we're writing out the chemical formulas like this, what did we just learn a slide or 2 ago? Carbon comes first, and then hydrogen comes next, and then we add in the other stuff following, right? So what's this guy here in the middle? And I'm spending a little bit of time on it because he is very, very important with respect to understanding a critical aspect of the way hydrocarbons work that is very easy to lose when everything is drawn like D or even worse, E. So,
The ball and stick model with three-dimensionality.
right, it's attempting to draw a flat molecule, a flat sheet of paper, right? But it's giving you dimensions. And so here you have, instead of just 4 lines, you have one that's a solid triangle and one that is a dashed triangle. And what that means is the solid triangle is actually coming out towards you. It's coming away from the plane of this page. And the dashed one is going back into the background. It's going behind the plane of this. So what does that imply about these 2 lines? Where are they located with respect to each other? They are on the same plane. And so if we were to lay this molecule down, then these 3 atoms, the hydrogen, the carbon, and this second hydrogen over here, would be on the same plane. And by that I mean a sheet of paper, or the surface of a table, however you want to define what a plane is. How many points does it take to define a plane?
3.
Pulling some geometry into chemistry here. 3, right? 1 point is just a dot, 2 points is a line, 3 points gives us a plane, right? So, a 2-dimensional surface, X and Y. Here's our X, here's our Y, whatever, however you want to look at it. You've got the same plane. And so these other 2 things, instead of just being a couple other lines, which implies that they're all on the same plane, right? Except that it's not. We should know, you should be able to recognize the difference between C and D because they are both representing exactly the same molecule. But what C is attempting to do is show you how 2 of those hydrogens are on the opposite plane, the opposite and perpendicular plane to the other 2 hydrogens. Now remember when I had you guys understand the way that tetrahedral worked was by holding up 2 peace signs and then doing something that some people might feel was mildly inappropriate with them? 2 of them form a plane, horizontal with the ground, and the other 2 are pointing up from the ground and down into the ground, right? Those are the 2 that we have drawn right here. One pointing up towards us, one pointing back away from us. This is going to come into play later when we start to appreciate the actual shape of these molecules. Right now, it doesn't mean that much, because what's the difference between this hydrogen and that hydrogen? Absolutely nothing. But as we start combining and getting at larger and larger hydrocarbons, that's going to have a very significant impact. So here we have another hydrocarbon, ethane. This was methane, 1 carbon, ethane, 2 carbons. But instead of C2H8, where would that have come from? Why would I think for even a moment that ethane, a 2-carbon containing compound, would have been C2H8? Why would I think that? What was methane? CH4. Right? So if I just double that, that would be C2H8, right? But that's not going to work. Why not? Because CH4, every single carbon, is already holding hands with as many hydrogens or other atoms as it wants to, right? So when we move up to 2 hydrogen or 2 carbons, one of those, each of those carbons is replacing one of the hydrogens that it would have been holding on to with the other carbon, right? Is this carbon still holding hands with 4 other atoms?
Yes.
Yeah. What about this one at the beginning? Is that holding hands with 4 other atoms?
Yeah.
Yes. Or perhaps I should rephrase. Does it have 4 bonds with other atoms, right? So far we're talking about saturated hydrocarbons, otherwise known as alkanes, but we'll get to that. So ethane is C2H6. Once again, here we have our space fill. our ball and stick, our wedge dash. So which of these hydrogens are on the plane here? We've got this hydrogen here is on the same plane as this carbon and that hydrogen. But the other four, these two up here and these two down here, are pointed either towards us or away from us. Now, something that I want you to appreciate that we're not going to spend a lot of time on, but I want you to appreciate that it is possible, is if we actually made this model right here with a bunch of balls and sticks, I want you to appreciate that all of these bonds can shift. It's like having things connected with ball bearings. The ball bearing can always turn, right? So when I take these two models right here, if I could reach into this and pull out a three-dimensional model, I would be able to hold on to the back of that carbon, almost like it's one of those back scratchers, like those handheld massage thingies. It's like, it's got to get right there. I could hold on to the back of that, and I could grab the other side with my other hand, hold on to the back of that. And I want you to realize that I can take those two balls and I can twist them. I can rotate them on the axis that is illustrated by that bond right there. And what that means is that when we draw this like this, this is the hydrogen that is pointing out at us, and this is the hydrogen that is pointing out at us as well. But I can also take this thing on the right and I can rotate it just a little bit. And suddenly we could get this hydrogen, instead of being behind the plane, we could turn it so that it's now in front of it. So we have two hydrogens pointing around otherwise. We could rotate these molecules because single bonds allow for spin. A single bond is not locked. A single bond always allows for rotation unless something else stops it. We can draw this like this, and the only reason why, or I should, all right, let me ask a question that's rather ahead of the box, and even possibly outside of the box for as deep as we're going to get here. But let's imagine for a moment that I did take this thing right here and I pulled it out of the screen, and I rotated this so that we did have these two hydrogens pointing out in the same place. So instead of being opposite each other, so this one's pointing out at us, that one's pointing out at us, that one's back, this one's back. If I were to take those two molecules and do that, I can tell you that that is possible, but if it was a real molecule, if I took a real molecule of ethane and just kind of zoomed in on it or made it huge so that I could manipulate it, I could twist it to do that, but the moment that I let go, it would pop back to the formation that it was before. Now it might spin back the way I had it, or it might keep going and go around a bit, but why would it pop back to where they're opposite each other like that? Can somebody tell me?
To maintain the repulsion between the hydrogens.
Those hydrogens have positive charges, right? And the electron density between the hydrogen and the carbon has a negative charge. And so these molecules are going to take a shape that makes those negative charges as far away from each other as possible, that puts the positive charges as far away from each other as possible. That's why in that original molecule we had that 109-degree bond angle between all of those hydrogens. That was to get all of those hydrogens as far away from each other as possible, right? The same thing is true here. Now that doesn't mean that it can't spin. It can. With just a little bit of energy, it can push past that repulsion and then either go back to the way it was or spin past it and have a slightly different orientation. But does that matter here? If I were to take this two carbon molecule and spin it, would it change anything about the properties of this molecule? No, because it would still just be two hydrogens with two carbons with three hydrogens each, right? But if we were to start changing any of those substituents, replace a hydrogen with, say, a chlorine atom, now suddenly it might matter. Is that chlorine atom pointed out towards us? Or is it pointed back away from us? When we start talking about the impact of these molecules from a biological perspective, the orientation of these bond angles suddenly becomes very important.
Is that isomers?
Yes.
Okay.
It's leading into that concept, yes.
Is this at all related to protein folding?
Yeah. It has everything to do with protein folding, actually. The same forces at work have everything to do with protein folding. So, alkanes. These are pure hydrocarbons. At least so far. Alkane is a term that describes large molecules made up of carbon and hydrogen. And the point of this section of chapter 11 is to learn the standardized naming convention that we have as a worldwide basis for naming which organic molecules we are describing. And so if you have learned what you are intended to learn from this chapter, you would be able to communicate in terms of chemical molecules with someone from Russia, as long as they understood chemistry. Because they wouldn't call it this weird thing that they have for a common name of something. They would call it the standard name that you have for that chemical molecule, which would lead to an interesting conversation where you didn't understand any of it, and then suddenly you heard a word that you recognize, right? It's like, listen to a bunch of Russians talking about Bob, and you get garbledy, 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 Bob, garbledy, 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 Bob, Bob, garbledy, garbledy, right? It's like, all I recognized in that was Bob. Unless, of course, you speak Russian.
In both Next Gen and Stargate SG-1, they ran into races that attempted to communicate, starting with the periodic table as the common language.
Yeah. To establish, like, here's the baseline.
Mm-hmm.
Right. Because it is a fairly intuitive way of organizing all of the elements of the universe. In the same way that if you like the movie Contact, the way it starts is by getting a signal that is not necessarily random radio waves, but simply a series of prime numbers, because only an intelligent source would be able to make a radio signal that only had a series of prime numbers. It's a little bit outside the boundary of what we're talking about now, but yeah, it's an interesting reference. So, how many carbons are there in this alkane? 5. 1, 2, 3, 4, 5, 6. Thus, C6H14. Now, if you had to, could you come up with the shorthand for a way to know, for example, what would the chemical formula be for a carbon molecule that had 10 carbons, assuming, of course, it was a saturated alkane?
Hexachloride.
Well, put numbers to it. It's 10 carbon molecules, so it would have how many carbons? C what? C10. H what? Well, think about it. How many hydrogen atoms do we have on this one on the end? 3. We have 2 ends, right? But all of the ones in the middle, how many hydrogen atoms do they have attached to them? 2, because the other 2 bonds are to the 2 carbons on either side, right? So a 10 carbon chain would have 8 carbons in the middle, right? And each one of those would have just 2. So that's 16 so far, right? But the 2 on the end would have how many?
6.
A total of 6, 3 each. So our 16 plus 6, 22. So it would be C10H22. Assuming, of course, we were talking about an alkane, I'm going to do this right now so that you can appreciate that this is important. And then I'm going to erase it because it's not the smartboard and it'll just stay there if I move on. But alkane is a name for a specific type of hydrocarbon that is saturated. Or more specifically, where all of the carbon atoms are bound together via what type of bond? A single covalent bond. I'm giving that to you now so that you can realize how important it is before we get to the part where it changes to mean something else. Well, a different word to mean something else. So, how do we name an alkane? Alkanes are hydrocarbon that contain only carbon-carbon or carbon-hydrogen bonds. Therefore, it's going to form a continuous chain. And so we have a standardized naming system, International Union of Pure and Applied Chemistry, IUPAC. And all of these guys are going to end in, why did I underline what I underlined? All of them are going to end in ane, A-N-E, ane. Just like alkane. Alright? We're going to use Greek prefixes as the thing that tells us how many carbons are in that chain. So it's going to be Greek something ane. Now this is describing the exceptionally simple case of alkanes where we have carbon, 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 hydrogen, so pure hydrocarbons, where everyone is connected via single bonds. So, here's a lovely table. If you don't want to memorize the order of these Greek symbols, does Columbia College have fraternities and sororities? No. No? Okay. So, a lot less of a reason for you guys to care about this type of stuff, right? You don't have any social groups that are requiring you to memorize the Greek alphabet and know individual systems. So you have methane, ethane, 3 is propane, 4 is butane, 5 is pentane, 6 is hexane, 7 is heptane, 8 is octane. Where's that come from? Where have you heard octane before?
Fuel.
Fuel. The octane rating, next time you gas up your car, look at the little number underneath the thing where it tells you the price. Underneath that, it's going to give you a rating. The octane is going to give you a rating for what the octane is, the ratio of octane, the purity of octane. Because we use primarily octane in our fuel for cars. On that subject of hydrocarbons and melting points, what's the natural state of octane at quote-unquote room temperature? Liquid.
But it's ammonia.
Yes, it evaporates quickly, but that's due to something else. It is not aromatic, but yes, it can evaporate quickly, but the natural form of it at room temperature is a liquid. It comes out of that hose as a liquid. And it doesn't immediately into a gas and get really cold, right? It's a liquid coming out of the hose, it's a liquid in the tank, and it's a liquid in your gas can, right? Yes, leave the cap off and it'll evaporate relatively quickly, but all that means is that the energy it takes to turn it into a gas is relatively low. Octane is 8, nonane is 9, decane is 10. It keeps going. Now here we have the molecular formula where we write C10H what? What did we say? 22. There we go. So this is the molecular formula here. We have the condensed structural formula. We're just drawing all this out so that we can appreciate what? That we have a CH3 at the beginning, a CH3 at the end, and everything else is CH2 in the middle. Now that becomes more critical later when we start talking about modified alkanes, where we're going to take some of those hydrogens away and start putting on other things like other hydrocarbons, or maybe some bromo, or maybe some chlorine, or maybe a nitrate group or an oxygen, things like that, but that's when it starts getting a little bit fuzzy. This is the line angle formula. We draw two of them together. We have our methane here with just 1 carbon, but if we have this guy right here with 2 carbons, we should, this is off by 1. Line angle formula. Each point in this line is 1. So we have 1, 2, 3 carbons. So I don't like this. One, 2, 3, 4, 5, 6, 7, 8, 9. Oh, they did do it right. 10. Okay. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Problem up here is this one's supposed to have only 1 methane. It's that guy, and then who's that other guy? So where did we get it? Where did it slip down? Because if we started off by 1 back here, then we should be good all the way down. Because this is actually 2, 1, 2. This is 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this is 10.
In programming, we call that a fence post error.
Yeah, because of the boundaries of the 1. Right.
If this is the first 10, how far does it
Yes.
go? Like forever?
Yes. Now, here's the thing. And this is the nifty thing about carbon. As opposed to silica, which is right beneath it, which also has 4 electrons in its outer valence shell, which therefore means it can also form 4 bonds. It wants to, it has 4 hands to hold hands with people, right? Because it needs to share its 4 with 4 more to fill up with 8, right? The thing about carbon is carbon can form, and this is only a euphemism because anything in reality that uses the term infinite is a euphemism. But carbon can form a near infinite number of bonds and shapes. But that's because carbon is just the right size to do it. Silica can't do that. Silica gets up to about 8, 9 in a row and it starts to break down. You can form silica crystals, but silica chains like this just don't work. Really big silica chains. Really big carbon chains though, they can just go. Now, the thing is, you're not really going to find them very often. Because most of the time when you find these really, really, really big carbon structures, they are either forming a lattice, so they're actually forming a crystal, as it were, or they are actually polymers. And so what you can do is you can look at that structure and instead of saying, that's 4 million carbons in a row, you say, well, that's actually this little unit repeated over and over and over and over and over and over and over again. But is there a limit? No, not really. I mean, a carbon nanotube that gets long enough, if it's not appropriately supported, would eventually break, thus shortening the molecule. But in a vacuum without any other stress, these guys can just keep going.
Your line angles don't line up, that's why. They're not lined up all the way.
Well, right. It breaks here at 1, but when we move on, so 3, 4, this is 2.
No, look, line it up. It's, the white line goes all the way across and then,
Yeah, but see, this is supposed to have 2.
yeah,
And then when we go all the way up to here, the example listed is not 2, it's 3.
I know.
I
Yeah.
think she might be implying if you're to draw
If
a
you
line
drop
down
those
between the
down,
carbons, that they may not. Well, that one, you have to leave that one alone. Well, no, I guess that one
Yeah, I don't know.
was. Well, is that just because, is it arbitrary?
No, it is not arbitrary. That is the way it is because that represents the 109-degree bond angle between the 2 carbons. So, but the point is that this makes it look like it's linear, right? If we move on beyond the fact that there's some problems with graphical editing of this thing here, this would be, if you were to draw this with a stick, this would just be 2 carbons. This wouldn't be 1. So,
I think we're just going up twos.
So, point is there are condensed structural formula here, and of course the molecular formula could very easily imply it. That you're dealing with 10 carbons that are all in a row, right? Because we could also draw it like that, couldn't we? Which is, the same as this. But we can get some other ones where we actually fill in the space, flat, where it looks like it's a nice straight line. What I want you to appreciate is there is no such thing as a straight hydrocarbon. Because every bond in a saturated hydrocarbon is at 109 degrees away from the next one. So every one of them is at an odd angle. Literally odd, 109 is odd. It's at an angle, it's not straight. Now that is true for alkanes. That is not true for all hydrocarbons, period. Because we can get carbons to make a straight line. Very, very carefully. But not when they're all saturated like this. So, our condensed structural formula is where we have 2 CH3s on the opposite end and 2 CH2s in the middle, but that is a total of 4 carbons, and that makes it a butane molecule. You can take this exact same model and add or subtract from it as much as you need. If this was simply ethane, then we'd remove these two things and we'd have CH3, CH3, right? If it was pentane, we'd have a few more of these CH2s in the middle, right? Here's the one that gets tricky. When we start talking about our condensed structural formula and expand them to show the bond, when we have our CH3 drawn like this, with our CH2s drawn like that, that's when it starts looking like we have this really large molecule that's in a nice straight line. And I need you to appreciate that that is never the case with respect to alkanes. Because every single one of these bonds is 109 degrees off from each other, right? And if we force all of these down onto the same plane, can you have what you get when you add 109 together 4 times? Do you get more than 360? Which is the limit of a circle on a plane, right? These are not flat. One pair of them is coming off of the board, bending at an angle. So, this is also a molecule with 4 carbons. Why? Because this crooked line has how many points in it? 1 here, 2 here, 3 here, and 4 here. So each one's going to have a carbon on the end, and then every carbon in between is one of those joints. Now, what we don't draw on this shorthand version is the hydrogens. So this carbon right here looks like it's only holding on to that carbon and that carbon, right? It looks like it only has 2 bonds. And that's because in the shorthand of organic molecules, if it's just a carbon-hydrogen bond, you don't bother to draw it. And so if you ever see a carbon in one of these guys that isn't holding on to 4 other things, you assume that however many extra partners it needs to fill up that outer shell, it's hydrogen. So this guy at the end is only holding on to 1 other carbon, right? So that means it has 3 free hands to make 4 bonds. So how many hydrogens does it have? 3. We don't draw the hydrogens here. We don't have their own little sticks. But in this shorthand for drawing the molecule, for an organic molecule, we assume that any unfilled bonds are filled with hydrogen. And once again, what would we call this? Since the name has disappeared from the previous slide, what would we call this organic molecule? Butane.
Quatrain.
In a different dimension. Alright, we can represent alkanes in all of these. We've seen all of this before. It's just a list of the A, B, C, D, E that we had before. And so it looks like this. Here's our expanded structural model. This is the one that is deceiving with respect to shape. All of the rest of them can be as well. This one down here at least lets you know that things are bending at weird angles. But we can draw that exact same 4-carbon molecule in virtually any shape. It can be a straight line, we can take a 90-degree turn, then another 90 degree, we can bend it 90 degree twice in a different way. All of these are equivalent representations of butane, because all of them are showing you a 4-carbon hydrocarbon that is fully saturated with hydrogen. And we could also draw it like this. What's the difference between these 2 line angle formulas? The only real difference is, did we start by going up, or did we start by going down? Right? But there is a special type of alkane that does not follow our previously established order where the 2 carbons on the end have 3 hydrogens and every carbon in between has 2 hydrogens. we can in fact form a line that never ends. We can take, say for example, 3 carbons, and instead of getting propane, which is just the name for a 3-carbon alkane, right, from that table, methyl ethyl propyl, right, so propane, this is propane, 2 CH3s on the end, and a CH2 in the middle. All of the carbons are holding on to the maximum number of hydrogens. But we could also make cyclopropane, where we instead take those 2 carbons on the end, and instead of holding on to a hydrogen each, now they hold on to each other. Are all of the carbons in this 3-carbon molecule holding on to 4 other? Are they sharing 4 bonds each? Yes, each one is holding hands with 2 other carbons and 2 other hydrogens. So all of them are nice and comfortable, all of them have a full outer valence shell. But instead of having a line, now we have, well in this case, a triangle. And so it's the same thing, it's still propane, right? Which tells you that there are 3 carbons, because that is the central and most important thing about any hydrocarbon is how many carbons. So it's still propane because that tells us it is a 3-carbon hydrocarbon, right? A 3-carbon molecule. And it tells us the ane part of that end, what does that ane right here, the ane, what does that tell us? That it's an alkane. Therefore, all of the bonds are single bonds, right? But the cyclo bit is the part that tells us there is no beginning. There is no CH3 at the beginning and CH3 at the end. Every one is CH2. So we have to lose 2 hydrogens to form that single bond right there, which is why instead of C3H8, we have C3H6. Here's cyclopropane, here is cyclobutane, here is cyclopentane, here is cyclohexane. And what do you notice about every single one of the carbon atoms in all of these shapes? How many hydrogen atoms does it have attached to it? 2. Because it's in a ring. Every single carbon is holding on to 2 other carbons as well. That gives it only 2 free hands, to use my metaphor, to hold on to some hydrogen atoms, right? We'd make a triangle, we'd make a box, pentagonal, hexagonal shape. Once again, normally, all of these bonds allow for rotation, right? And I don't just mean between carbon and carbon. I could take those hydrogens right there and I could twist that hydrogen, I could spin it like a top. Because it doesn't matter, right? But now that we formed a ring, can I take that carbon right on the end and can I twist it so that the hydrogens are pointing in opposite directions? Can I do that? No. Because they are locked in. Those 3 carbons are now forming a plane. Now those 4 carbons right there are not forming a plane. I want you to appreciate that. 3 of them are. Pick any 3. These 3 right here are forming a plane, but that 4th one is either going behind or in front. Everybody follow? Because once again, 109-degree bond angle, right? You can't fit all that on one plane. But these are all still alkanes. How do we know that? 2 reasons. 1, it tells us in the names, right? Up at the top there's an A and E at the end. But we could also just look at those structures. Do you see anything other than single bonds there? Nope. So what's important when you're naming an alkane? Number 1, how many carbons? Number 2,
Single bonds.
they're all single bonds, right? And so the next thing that matters is it linear or is it circular? Is it cyclo? Is it a cycloalkane or is it a linear alkane? Because the difference between pentane and cyclopentane is a big difference, right? It changes the number of hydrogens that are there, but not the number of carbons. Pentane is pentane, regardless of what shape it takes. Which by that meaning, I can take this cyclopentane right here, and if we actually had that in a ball and stick model, I could bend those things so that carbons are pointed out and behind, but it would always, there'd be a limit to how much I could bend those things, right? Because if I bent it too far, I'd snap one of those connections. But all of those carbon atoms can still move. They can shift those angles, they can kind of bend around each other to a limit. And why is there a limit? Because it's cyclo. This guy back here, that carbon right there can spin freely. That carbon right there can spin freely. This carbon can't spin because it's locked in a ring. This carbon can wiggle, but still can't spin because it's locked in a ring. Alright, so let's talk about some alkanes where we start getting kind of tricky. Are those two molecules exactly the same thing? No. And yet, how many carbons do they have?
4.
They both have 4 carbons. But wait, they should have different number of hydrogens then, right? So here we have 3. Another 3 over there makes 6. 2 more here makes 8, 2 more here makes 10. How about down here? We have 3, 6, 9, 10. Crap. It's C4H10 both ways. But are they the same molecule? No. Especially when it comes to biological systems, which is why we call this organic chemistry. These 2 molecules could be very, very different with respect to what they can be, what can interact with them, what can digest them, what that might be poison because of them. So, here we have the introduction to the idea of a structural isomer. The same molecular formula, C4H10, but different organization. In this case, do we have a straight or do we have a branched chain? It's still butane with respect to naming of the alkanes here, because there are 4 carbons, and it's the same number of hydrogens. But it can have 2 different structures. When we talk about substituents or substitutions, what we're talking about is replacing some of those hydrogens with something else. If we replace it with other alkyl groups, then that means we're just adding more carbon on, but now we're making a branching carbon structure instead of a strictly linear one. Now we're adding extra carbons on somewhere. In the same way that this is a 3-carbon chain with a 4th carbon attached to the middle, right? Whereas this is a 4-carbon linear chain. Everybody follow? But instead of attaching a carbon to the middle there, we could have attached something else, like a chlorine, or an iodide, or really anything else. So, we change the ending there when we have alkyl compounds, where we have different alkyl substituent groups, other carbon substituents, and then we have halo substituents, where we add fluoro, chloro, bromo, or iodo to the name. So knowing what we already know, what would this be if instead of adding that 4th carbon here, we would have added a chlorine atom? What would this be? Chloro, we're good so far, but how many carbons are there? If this is chlorine instead of carbon, there's only 3 carbons now, so it would be chloro what?
Three.
3N, yeah, there we go. Well, let's go back. What do we call something with 3 carbons? Propane. So it would be chloropropane. Because there's 3 carbons. Now, that's not quite right, and we'll see why here in a minute, because chloropropane tells you what about that molecule? This hypothetical molecule that I'm introducing you to. It tells you that there are 3 carbons, right? How do you know that? Because we're calling it propane, right? It tells you that it's all single bonds because we have an A in there, but we know there's a chlorine. Okay, where's the chlorine? Do you know that yet? If we just call it chloropentane or chloropropane, do you know where that chlorine is? Do you know which carbon that chlorine is attached to? It could have been one of the ones on the ends. I mean, we described it as being the one in the middle, right? But would it still be propane if it was attached to the one in the beginning and still only had 3 carbons? Still be 3 carbons, right? So it would be propane. So do you think maybe there's more to it? Of course, there's more to it. So let's get back to where we were. So if we're adding groups, we can say add a methyl group, that's an alkyl addition. We can add an ethyl group, that's another alkyl addition. We can add a propyl group, that's another alkyl addition. We can add an isopropyl group, which just means we're adding a propyl group where we bonded it to the middle, which is what we were just describing, right? So now that propane, the propane that we were looking at could be not even just its own molecule, but it could actually be an alkyl addition to a different, even larger molecule. And then, of course, we could have fluoro, chloro, bromo, iodo. All right. Let's talk about how you would change things if you are substituting off of a ring. So this is a cycloalkane. How do I know that? Because the slide tells me. But how would you know that? Because it's in a circle, cyclo. It's not linear, right? It connects back to itself, which makes it a cycloalkane. How do I know it's an alkane?
It's all single bonds.
It's all single bonds. Cycloalkane, right? So, how many carbons are there in that center ring? In the circle, the cyclo thing. How many carbons are there? 1, 2, 3, 4, 5, 6. So this would be cyclo what? Hexane. But we have a what attached to it? How many carbons are there in this thing attached to it? 2, which would make it a ethane. Oh, well, yes, a total of 8 carbon molecule, but this is an ethane addition, right? So that's how we get the ethyl cyclohexane. How would this be different if this was a... This is going to sound a little bit weird, but follow me here. How would this be different if this was an ethyl hexane? It'd be linear, right? Follow me here. Let's take this guy right here, and let's break it. And instead of reconnecting to this up here, let's make it come down here like this. So this guy's not here right there. What would you call this molecule? This would be our ethyl hexane, right? No. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I've drawn it this way, this is not hexane anymore, because this is one linear molecule, right? We start here, we end here. So this wouldn't be hexane anymore, it'd be nonane. But I don't have to break it there. What if I break it right here? If I break this guy right here and bend it this way. Now we have 1, 2, 3, 4, 5, 6, 7, or 5, 6, 7. Well,
It's an iso.
this would be a 7 carbon chain. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, right? With a 2-carbon chain attached to it somewhere. Different naming conventions for different molecules that take different shapes. As it's drawn here, the most important part about this is the fact that it's a circular or cyclical molecule. And so we don't care about any of this other crap. The first thing we have to know is that it's a cyclical molecule. So it's a cyclo something. So the naming convention says we name the circle first, and then we name the other stuff. In a linear molecule, what do you name first? You haven't mentioned it specifically yet, but I have now hinted at it. In a linear alkane, what do you name first?
Number of carbons.
Not just the number of carbons.
Bonds.
You name the longest carbon chain. The longest linear carbon chain. Yes, it can branch, but if we get branches that break that linearity, then those have to come off. We have to name where those branches happen. I'm getting a bit ahead of myself, but I want you to see it coming. So this is a cyclohexane with an ethyl group added to it. Does it matter which carbon the ethyl group is added to? Would it change the shape of the molecule if we added it to, say, this one down here? In this case, it wouldn't, right? Because we just have one thing added to it. It doesn't matter where on the ring you add it to it. You get a ring with an ethyl group heading off the side, right? But what if I added more than one? We could add another one right here, or we could add it over here. Would those be different? Those would be different. So we need a way to tell the difference between those molecules, right? Don't worry, it's coming. So here's the summary for how you give names for these alkanes. The first thing you do, if it's not cyclo, is you find the longest linear carbon molecule. And that's your base, your 7-carbon chain, heptane. But in this case, we also have some other things hanging off of that 7-carbon chain. So we have 1-chloral, 1,2-dimethyl, heptane. The di means that there are 2 of them. The 1-chloro tells you where that chlorine is hanging off of. The 1,2-dimethyl tells you where both of those 2 methyl groups are hanging off of.
Wait, so what's the word for it? Chloral dimethyl heptane?
Well, that is,
Okay.
the full name is 1-chloral,
Okay.
1,2-dimethyl heptane.
Okay.
Now, I don't particularly like this name. It's a good example, but they really needed to do something different with this. And here's why. Let's draw this. So, it's a 7-carbon chain, so let's try drawing this. 1, 2, so 1, 2, 3, right? Because I now have three points in this, right? 3, 4, 5, 6, 7. So let's call this one number 1, right here. So where's the chlorine attaching? It's attaching to the first one, because that's what the 1-chloral means. So we also have dimethyl, 1,2-dimethyl. So where would those attach? Well, one of them is going to attach right here, right? That's the 2. But where's the 1? Where's the other one? The other methyl? It would attach right there. You see a problem with this? I see a straight line connecting this carbon to this carbon, following that backbone. So another name for this could actually be, from our very overly simplified understanding of the naming system, this wouldn't be heptane, it would be octane. 1, 2, 3, 4, 5, 6, 7, 8. But instead of that, it would now be, if that was true, that would make this one over here the first carbon, this would be the second, and this would be the third. So rename this for me. What's the name? If we take it starting from here, there are 8 carbons, so this is now not heptane, but what? Octane. Where's the chlorine? On which carbon? The second one, so it would be 2-chloro. Where's the methane? On the third one now, right? So 3-methyl octane.
So chloral 2-methyl octane?
Well, this would be 2-chloral 3-methyl. Because that methyl group right here is actually on the very first carbon. So it makes it an octane. But the point is that both of these things are naming the same thing. You could name it either way, and it would describe the same molecule, right?
So if it's 3-methyl, would be trimethyl?
No, it wouldn't be trimethyl, because what we're doing is we're taking away this one and making it part of the octane, which leaves us this guy, but now instead of being attached to the second one, it's now attached to the third one, because one of those methyls became the number 1 carbon, the first carbon in line, which is why the chlorine was attached to what we called the first one before. Now it's attached to what we're calling the second one.
Yeah.
So it would be 2-chloro, 3-methyl octane. So that's an introduction to the naming system for alkanes. It's fairly easy to anticipate that there will be something to ask you, not so much how to draw something, but what is the appropriate name for this molecule? You could recognize an alkane based on the fact that everything's single bonds, right? And then the rules are, is it a ring? And if it is, start there. If it's not a ring, find the longest chain and start there, right? Or another way you could do it is look at all the possible answers and find the first and rule them out as they don't work. If it says 4-chloral and there's no way you can look at that molecule and put the chlorine on the 4th carbon, then that's not right, right? All right, so let's talk about some properties of alkanes. If you're talking about an alkane with 1 to 4 carbons, then they tend to be gases at room temperature. Where do you get butane? What do we do with butane?
Burn.
We burn it. You guys ever refill the butane lighter?
Yeah.
We get it in a canister. If you push the tip of that canister and open it up, you get a bunch of liquid pouring out. Comes out as a gas.
It's under pressure.
Right, unless it's under pressure, which would refer back to those rules that we learned earlier about pressure and volume changes, right? Because we didn't really talk about change of states and how that applies, but yes, under pressure, something might be a liquid instead of a gas, right? That's why the butane lighters that you can buy, they're kept in a canister. If you're talking about something with 5 to 8 carbons, now we're talking about something that's a very volatile liquid at room temperature, which makes it very useful as long-term and more energetic fuels. So this is where our octane comes in. Pentane, hexane, heptane, octane. Octane is the largest hydrocarbon, therefore the most energetic, right? Because the more carbons we add to it, the more possible energy we are storing in this hydrocarbon. But if we get bigger than octane, guess what starts to happen? If these are gases at room temperatures and these are liquids at room temperatures, 9 to 17 tend to be thicker up to and including solids. Solids and semisolids. So 9 to 17 are liquids with higher boiling points. That's our motor oils. 18 or more and you start getting into waxes. petroleum jelly, Vaseline, semi-solid mixture, more than 25 carbon atoms linked together.
So are these all naturally occurring together? Do they have to somehow reduce or separate? Because I mean, natural gas, kerosene, petroleum jelly, paraffin, they're all harvested from this sort of the same.
Okay. Natural gas comes from natural gas deposits because it naturally occurs as a gas. So we frequently get some methane and some propane, some ethylene in there, but those have to be purified and separated. But you don't get so much natural gas coming out of an oil vent unless you're careful about controlling it, because those are stored as liquid deposits. Now, you do get a lot of different hydrocarbons in what's called crude oil. So the liquid oil that comes out of the ground, that comes from organic deposits from millions and millions of years ago, those didn't end up that way because plants were smart and thought that, you know, millions of years in the future, humans would need them to have an octane orientation. And so when we pull natural crude oil out of the ground, we have to purify it, and that's why crude oil doesn't go into your car. Crude oil goes to a refinery, and that refinery takes the crude oil and it separates it out into its component parts, and the purified octane is what gets sold as gasoline. But that same crude oil is where we get these larger carbon units, 9 to 17, which we then sell as motor oil. So we purify out the different constituents of that mixture that we pull out of the ground. All right, more properties of alkanes. Alkanes are nonpolar. We know this. We could actually calculate this if we needed to, because we could go back and look at the electronegativity of carbon versus hydrogen and find out where it falls on that scale and determine that it's a very only borderline electronegative bond, and so the electron density is going to be pretty much evenly shared between carbon and hydrogen. And the fact that all of the bonds we're talking about are carbon-carbon or carbon-hydrogen bonds means that we're not going to really form dipoles anywhere, which means that we will be very, very, very nonpolar. And what do we know about like and dissolving of like when it comes to polar and nonpolar substances? The fact that like dissolves like, right? And so water is polar, alkanes are nonpolar, and so they do not mix well. They are insoluble in water. Also, the vast majority of them less dense than water, and therefore that is why oil spills float. Now, there are some examples of oil spills that didn't float so much, like back in the deep horizon, right? So what's going on with those? Well, those aren't pure substances. As the oil was coming out, we did a lot of things to that oil, including mixing it with other chemicals that attempted to act as surfactants or otherwise, which changed the way in which it mixed with water. And so between that and the regional density of the water in the area, you can get pockets of oils and hydrocarbons that didn't just rise to the surface. But where do we spend most of our time trying to clean up an oil spill? At the surface. Because the vast majority of those hydrocarbons coming out of that well are going to float.
Waterfowl are very absorbent, they're good for us, you know.
Yes, those feathers have a lot of space to hold those nonpolar hydrocarbons. So they work just really good sponges. You're right. Not very efficient though. They're not very reusable. It's kind of one-time use. Unless you want to spend a lot of time cleaning them up afterwards and sending them back out. Yeah. Well, do we finish that? Lessons in water. Flammable in air and found in crude oil, since that's the source here. Flammable in air. They're also flammable in liquids if the liquid happens to be pure oxygen. Point is that these things react with oxygen and produce a lot of energy. Combustion. Alkanes with strong carbon-carbon bonds react with oxygen in a combustion reaction is exactly as we have previously described, which produces carbon dioxide and water. We break those carbon-carbon bonds by interacting with oxygen. So here we have CH4 interacting with oxygen to form CO2 and 2H2O. Of course, this is a bad example of breaking high carbon-carbon bonds because we're dealing with methane that doesn't have any carbon-carbon bonds, but still the idea is the same. We're taking hydrocarbons, reacting them with oxygen to replace the hydrogen that is holding on to the carbon and instead replace it with oxygen and then creating water. That act releases a lot of energy. Methane, otherwise known as natural gas, CH4, methane, releases a lot of energy, but not so much that it's exceptionally explosive. And so we use this for cooking of our food and heating of our homes. Natural gas is not the same thing as propane, which is why if you ever become a homeowner, if you are a homeowner and you do not have electric heating, the difference between a natural gas heater and a propane heater is a very important thing. Usually the people that you might call to refill your heater are going to be smart enough to like, well, I'm running out of whatever go juice my heater uses. They're going to tell you how to figure out what it is. When you buy the house, they're going to tell you what type of heater it is. But it would take an exceptionally stupid and honestly probably a mechanically challenged or gifted person to put propane into a natural gas container or vice versa.
See, people heat their homes with those nice little portable things used for camping and stuff.
That's true.
And then wind up dead.
Beggars can't be choosers sometimes, especially when the power goes out. When I was living out at a state park and the power went out for 7 days during an ice storm. That was fun. It took them 7 days to come back and get the power back to the park. And so for 7 days I was going to work in my heated car, driving home and spending the evening until the sun went down chopping firewood, and spending the night not so deeply sleeping next to the fire so that I could wake up every 2 hours and throw a few more logs onto it to stay warm. It was after that we got a space heater, not propane.
Kerosene.
Yeah, kerosene space heater. So that we could fill that up and sleep not on the floor, but still where it's still warm.
Don't sleep on the floor.
We didn't sleep on the floor then either. We had an air mattress to keep us off the floor.
Oh
but
yeah,
still,
that's so
like,
much better.
Yeah, I mean, well, 6 inches can save your life.
That's true. But if it's not venting, it can rise.
Yeah, it'll fill up the room. Eventually it will fill up the room and you won't be able to tell. Why? Because carbon monoxide is odorless! Remember we learned that a while back. Right? You can also get little butane things. So if you go to buffets, like catered buffets sometimes, catered events, there are a couple of different ways that they do it. Some of them have just literally little like paraffin wax candles that they put underneath it, burns nice and hot, and it keeps the tray warm. And some of them have literal butane stoves, and so they've got literal butane heat source underneath those trays, keeping them warm for you.
They also use stir now.
Yeah, that is an option if you're particularly. Well, they're not even Boy Scouts anymore. I was going to say particularly Boy Scoutish. They're not even the Boy Scouts anymore. So, here we have burning a 4-carbon butane molecule with 2 of them together with 13 molecules of oxygen gives us 8 molecules of CO2, 10 molecules of water, and a crap ton of energy, which in this case is being used to warm up the water in that pot, and also the air around it, because we're not good at capturing that, but hey, close enough. Alright, so, everything so far has been about straight chain, single bonded carbon molecules. And when we get back from taking a short break, we'll talk about the other guys. Because it's 7 o'clock. So, take a break, stretch your legs, get a drink, what you need to get.
Did you say emotional support animals are okay?
Would I say they're okay?
Did you say they were okay? I thought I'd asked, but I can't remember.
I don't have a problem with emotional support animals. I think that they need to be regulated. It's a bit of an off-topic question.
No, that's
For the classroom?
our air conditioner on.
Oh! Honestly, that's a...
Bring it in, bring it in.
She said it's fine. I don't have a problem with it. I am unsure as to the university policy, but I'm pretty sure if it's an actual emotional support animal, that it's allowed. Pretty sure.
The teachers bring
So,
theirs.
from an HR perspective,
Yeah?
Yeah.
there's no certification to an emotional support.
Yeah, exactly, which is why you get like emotional support camels.
So, you can, well, the
Peacocks.
number two biggest, like the number two emotional support animal, past the dog, is a miniature donkey, or a miniature horse. Because they live longer than dogs.
Right, yeah, so if you're gonna get a nice emotional connection, you wanna do it with something with a long lifespan. And everybody knows that parrots are just bastages, so you wouldn't want to do that.
Anyways, it takes a long time to train a dog, and they don't live as long, but you can train a miniature horse the same thing, and they'll live 30 years.
You could train a parrot that way, and it'd live to be 160.
Birds are worse.
Yeah.
But for the university, the disability resource centers, you would have to connect to it to get your reasonable accommodation period.
Well, I've got,
For tonight, I don't know.
my psychiatrist is really odd. He thinks he has to write specifically for the location, and no, that's not how it works. But, so, I've registered at NU, I can bring her in. I haven't pursued it here yet.
Is it a dog? Is like, can I pet it?
Yes, she's,
So now she's training.
my,
Well, usually when they're working, you can't pet her.
Right, that's a
Oh,
different.
no, no,
It's supposed to.
Yeah.
no, it's her 3 weeks ago, my primary ESA passed away. She's still a puppy, and for some reason she's terrified
But people,
of everything but other dogs. And with other dogs,
are you
she's,
sure you would like to bring an unstable emotional support animal into the classroom?
Right.
Wait, you have a puppy in the car?
With the AC on it. Your car's been running this whole time?
Right.
I didn't have time to take her home. She needs a lot of emotional support.
Try to be back in 5-ish minutes.
But isn't the emotional support animal?
Wait, we need time. We
Right.
need time to see this dog.
But I mean, I can understand dogs needing a.
There will be time at the end of class. I don't think we're gonna get all the way in.
Situation.
I'm intentionally trying to spend a lot of time on
Right.
this subject, but
That would
we
be
could
I
have
thought
finished
you
this a
meant
lot
like
faster
it
if I just burned
like
through
the
it.
dog needs emotional support.
Yeah, but you don't get a lot
I
of
was
support
representing it as
that.
for him.
Yeah.
Whatever.
Yes, I assume it is
That's
for
it.
him, but it's still in training.
There's no regulation on an ESA.
Right, which is, that's the part that I think needs to
You
change,
can
but.
print off a, like, emotional support animal badge on the internet for $7.
So actually,
Oh,
yeah,
really?
yeah. So actually, once upon a time I did that because my landlord was like, you have to get rid of your dog, and I was like, I should
And then you're
already
just
been.
like sucking.
She had already been living with me, and like I mean like my dogs are my life. If you
My
can
dogs are
tell.
my babies.
Like my whole computer.
It's okay.
I have more pictures of my dogs than my
And-
kids.
Right.
Aw.
And so I went and got like one of those ESAs online, and they denied me.
What?
Like my landlord was like, "This is fake."
But it's not.
It is.
Yeah, but
It is
there's
fake
no-
because so to have an ESA, you have to like to have an actual ESA, like to be cleared by like actually be cleared legally with it. You actually have to go see a physician and be like qualified as having like disabilities, and it can't be like you can't go to your doctor and be like, I have anxiety. Can I have like
I
you
mean,
have
I'm
to
sure
have
you'd be
like
surprised.
you have to. Oh no,
I'm sure you could.
they
Like,
will.
okay, yeah, I
They
bet.
will, but like they can go back and look up your history, like with like when it comes to legal matters, like if you were to try to take it to court or something, because I looked into like getting my landlord in trouble for it, and because it's like an online psychologist, it doesn't count.
But I mean, you could have.
Well, no, but they have the right to contact the doctor and ask if they've been taking care of you and how long. They don't have the right to ask like any medical questions about it,
Right.
but they have the right to be like, how long have you had this person, like things like that.
But if it's just cheerleading. I don't know how cool you are with your dog, because I'm pretty cool with mine.
Oh no, I have.
You know what I mean?
My oldest dog is an emotional support animal from my actual like doctor, but at the time that was like a quick like, my landlord was trying to kick my dog out for no reason, and I was like, yeah, no, this isn't gonna happen. But my dog actually was in training to be like a service dog, and then I stopped because like, it was family, and so I was like, this is kind of just torture to her.
See, my thing is, I have had some friends that did train,
Like service dogs.
service dogs and support animals, right?
My
And so,
father-in-law did too.